Shall we start, I guess? Well, good morning, everybody, and welcome to the last day of the conference. Very happy to have you here, and even more happy to welcome Professor van der Schaar, who is going to give the keynote of today. So let me introduce her. Professor van der Schaar, it is likely to be known to most of you, but anyway, he's the John Humphrey Plummer Professor of Machine Learning, Artificial Intelligence and Medicine at the University of Cambridge. And in addition to leading the Van der Schaar Lab, Mihaela is founder and director of the Cambridge Center of AI Medicine. Just let me say one last thing, if you want me to cut, because she asked me to cut, but I would like to mention that in 2019, an ESTA report determined that Mihaela was the most cited female AI researcher in UK. And I think this is enough to realize how outstanding she is. I'm very glad to have you here and leave you the stage. Thank you.
It's such a pleasure to be here, and I've been here multiple times, so that's the reason, no need for an introduction. Thank you so much, Francesca, for inviting me. It's such a pleasure to be here yet again in Milano and Politecnico, and it's especially amazing for me to be here now because I have students from all over the world, 19 now different countries from all different continents, but I never had an Italian. And starting in September, I'm going to have an Italian that comes from this university. Luca, say hello. Don't be shy. So I'm very, very thankful to you for sending along one of your brilliant students to me, and I hope he'll be one of many. So thank you very much. Okay, so I tend to talk a lot, and I have many slides, and I don't have a pointer, so hopefully this will work out in the time I have. My plan is to talk today to you about reality-centric AI, and this is actually a topic that I started to talk about a few years back, partially in a push to my own community, the machine learning community. I know you are a very diverse community, so this is a push to you, the machine learners in the room, because we are too obsessed with algorithms and improving algorithms rather than solving real-world problems. So I made this manifesto, which I call the reality-centric AI, partially to push the machine learning community to take real-world problems and try to solve them, rather than playing games of Go or looking at building algorithms that are really tested in very petri dish types of environments. If you are interested in this manifesto, it is on our website quite prominently. Take a look and feel free to email me and debate with me about this. What is reality-centric AI in a nutshell? It's very simple. It's AI that really aims to solve real-world problems and deals with the complexity and the messiness of the real world, from data, which is the subject of the talk, not of the talk necessarily today, but of the day of today, as well as building AI that is truly empowering for humans. And this will be quite a topic for me today. Over the 20-something years, somebody put me to write my birthday on the note. I'm like, oh my God, I'm at an age at which I like to lie about my birthday. Should I put a day, but cut 10 years from it? But I need to admit to you that it's 20 years plus that I started my lab in the United States. And over the past 20 plus years, we worked on many, many different areas. We worked on communication systems, we work on finance, we worked on smart city, we work on energy grids, and so much more. And nowadays, in the last 10 years, I really focused mainly on building AI for my passion, which is the area of healthcare and the area of education. And I'm going to hear still a quote from John Tucky, who is a statistician, not a machine learner. I steal his quote, and I put machine learner rather than statistician. But note that this quote is stolen from Tucky. And he says the best thing about being a statistician, Tucky, me, machine learner, is that you get to play in everyone's backyard. And I think that this is really an opportunity and a blessing, the fact that we can take real-world problems and see how, in my case, AI can transform them. And this is why I put this manifesto for reality-centric AI. So really solving human-centric problems is, I think, the biggest challenge in AI. Not coming up with a delta in terms of an algorithm. So from that point of view, this is kind of a message that I hope to leave you with. So our focus is really to take big and bold problems that have not been solved so far in healthcare and beyond, and try to formalize and define this problem for the first time, wrap our heads around it, and invent cutting-edge solutions to solve them. But that's only secondary. The biggest problem is to identify cutting-edge problems that need solving by talking with a variety of researchers as well as industry in different domains, understand these problems, and then formalize them for the first time. And there is usually a gap, because if you look at the computer science community and engineering community, they often, well, engineering maybe less, but especially computer science community, is used to having problems, canonical problems that are already formalized, and everybody works on these benchmarks, which is really not a good way to go about it. What ideally we want to do is to understand the real world, and I'm happy that I have so many young faces here, because I feel really the machine learning community has lagged behind in trying really to understand the real world and trying to engage with it and solve problems using AI in the real world. So that's kind of the message. And this is hard. This is hard because it's a lot easier to take an algorithm, tweak it a little bit, and show on a benchmark you are better. It's much harder to understand the messiness of the real world and define the framework to solve these problems. And really, where we come in as a lab is trying really to bridge this gap between the complex real world, which contains stakeholders from medicine and beyond, and trying really to build machine learning that is useful. What you will hear today, and this is a talk that I just put together for Francesca, so hopefully this will work out in the time I have. I'm going to talk to you about building large language model agents, and our lab has been one of the very first in the world to build LLM agents for the last 2+ years. Now you hear a lot about them, but when we started the journey, there were very few. And I'm going to show to you why I think that they are exciting to solve reality-centric problems. I'm going to give you 4 examples from scientific discovery, digital twins, code generation, and clinical copilots. And then I'm going to tell you why I think we shouldn't stop at AI agents. We need to go to what I call genius, which is the next generation AI agents, and why they need to work with each other, and why we need to move beyond the current internet to a new digital economy, which I call the agent network. And hopefully I end with a call to action from all of you, if I'm doing it on time. So all of you are using large language models, whether it's OpenAI or DeepMind, or for that matter, Anthropic. And you know that while large language models are fantastic text predictors, what is really exciting about LLM agents is that they can take a particular goal and then plan and execute and adapt in real time to execute this plan. Now, over the past years, we have done a lot of work on LLM agents. I'm going to show to you 4 examples, but there are many more. We were very early understanding, partially because we are interested in solving problems in the real world. When we saw large language models coming, unlike other people my age, I immediately jumped on the bandwagon because I was very interested. And for all the unconvinced people in the room, be convinced. It's an amazing technology, and it's an amazing technology because it enables us to bridge the world, the real world, with a world that's quantitative, whether it's mathematics, machine learning, or statistics. It's really an opportunity for us to solve problems in the real world. And hopefully I convince you that we can. I'd like to start with the first problem, which is using LLM agents to do scientific discovery. We hear a lot in the world now about drug discovery. That's important, but I'm not going to talk about drug discovery here. The word discovery is not actually so correct, in my opinion, when we talk about drug discovery. Well, maybe it is, but when Fleming discovered penicillin, he saw it works, but he didn't know why. What I'm going to talk about here is how can we use large language model agents to do true discoveries, to really try to understand fundamental laws, whether it's in medicine, which is the topic that interests me, and physiology, or for that matter, what I'm talking about here can be useful for other areas. And I know that Francesca is a mathematical engineer like me, so this talk is dedicated to her. And when I came here last time, which I don't know, it was not too long ago, 1 or 2 years ago, I talked about rocket science math to solve this problem. And what I want to show to her and to all of you is that unfortunately we no longer need math. We now need just being smart with large language models. So I want to show to you how we pivoted from math to large language models. And again, why do we care about that? Because it's useful. Dynamical systems are useful. The engineers in the room don't need convincing that dynamical systems are useful. But for the ones among you that come from other domains, including clinical domain, I'm going to convince you that everything in the world that's of interest is a dynamical system of lower or higher complexity. So why are we interested in discovery? We are interested in discovery because scientists over the ages, whether it's Einstein, Hill, or Kahneman, from the physics to physiological to psychological, they discover laws, which are governing equations, usually in high school. And in Italy, you have a fantastic high school, so you really learn some math in high school. At times, I go to different countries, including in the UK, I put this and they say, we don't learn this in high school, but I'm almost sure you learn quite a lot of this in high school. So you learn laws, and usually these laws, we learn them in physics, but they abound in other areas as well. So the type of laws that you see here are generalizable, they are concise, they are understandable for a human being that has a certain level of mathematical sophistication. And they are truly transparent. I'm not talking here about discovery that are black box, because what's that for a discovery? Discoveries are truly empowering for the human and understandable to humans. So what we are interested is to discover science. In my case, it's the science of medicine, but it can be useful for physics or other areas. And we are interested in discovering trajectories of disease. We are interested in understanding tumor growth over time. Or, for instance, spatiotemporal physiological systems and beyond. Okay. So what I'm going to show to you today is what LLM agents have to do with it. But I'll take you a little bit back in time to when I visited here last, because most of you were not here, to tell you how we used to be solving this prior to this LLM revolution. So the type of problem that we have is we have data. Very important, data, but data is real world, so it's messy, it contains errors, it's irregularly sampled, it has noise, it's limited, so real world data, and hopefully cutting edge machine learning models. And what we want to do is to discover from it these governing equations of dynamical systems. So we have a data set, and what we want to discover is transparent dynamical system from this data. I'm not talking here about neural ODEs. Neural ODEs, number one, don't work most of the time when you apply them to real world data. Number two, they're not a discovery, they're a black box. Very uninteresting. So what we are interested in is to discover dynamical systems from data. And again, why we care about it for the people who may not come from engineering, who may need a little bit of motivation. In medicine, everything is a dynamical system, whether it's a PK model, whether it's a PD model, whether it's a BPK model. So we do a lot of work with pharmacologists, which are very sophisticated scientists discovering this dynamical system from data. And we are working with them to empower them with machine learning. But other areas in which I don't have collaborator, and if you are a clinician in the room working on that, I hope to recruit you. For instance, regulatory models, homeostatic and non-homeostatic, epidemic and population dynamics, biochemical pathways, they are all dynamical systems. They are all represented through these ordinal differential equations. And also neurophysiological models. So why this is hard, why historically it has been hard to use machine learning and this complex data to learn these dynamical systems, is that these equations need to estimate derivatives, and estimating these derivatives from real-world data is messy and challenging. This has been, if you like, a very hard unsolved problem for a very, very long time. We have symbolic regression, but symbolic regression doesn't work off the shelf. We have two-step symbolic regression. It doesn't work well in most cases, so it was an open challenge. Luckily, I recruit smart students such as Luca, who can solve problems I cannot solve. I like to scout problems, but often I'm obsessed with them and not knowing how to solve them. Luckily, a statistician and a mathematician, Zhaoji and Christophe, were able to solve it a few years back. And this is the code, and this is work that I presented when I last visited Francesca. And what we did in this work, I'm not going to put any math in front of you, it's early morning, but I just want to tell you that we use quite complex mathematics to be able to solve it. So the way we were circumventing, estimating these derivatives, we did something that, it's funny, it's a statistician and a mathematician, they came up with the idea, but we did something that's very common in engineering. We did a change of basis. So what they realized is that we can change the estimation, this problem from estimating ordinary differential equation in estimating something that we can compute very easily because we transform this equation, this ordinary differential equations into solving problems using the variational formulation of ODEs into problems that require us to compute derivatives on very simple basis functions. So the idea is take something you don't know, which is complex, you need to estimate, use variational formulation of ODEs to turn it into another space, into another basis where you can compute because you design it like an engineer likes to do. Because you design it, it is easy to compute. So it's easy to compute derivatives. And in other words, you don't need to compute the derivative of the original signal, but rather the derivative of something you design, which makes it easy. If you are wondering what the hell is going on here, please take a look at the paper of Christophe and Zhaoji. But then it was quite complex math. We did it. And we said, well, go take this algorithm, which is a quite complex algorithm, but works beautifully and works. It's transparent and works a lot better than neural ODEs, which is quite amazing. But we said, well, we started a debate when the large language models came around a few years ago, 3 years ago. And some of my students said, well, what about large language models? Can LLM agents do this? Can replace the mathematicians and the statistician in the paper? And I thought, no way. But of course I was wrong. And an engineer this time, the statistician, the mathematician didn't want to deal with large language models at the time. And another engineer, so Sam is an engineer, Zhaoji is a statistician, Tennyson is an engineer, and also Jim Wetherell, who is the chief data officer of AstraZeneca. We started to see if we can use large language models to solve the same problem as the one that Zhaoji and Christophe has solved. And the answer is we could. And we could not only solve it, we could solve it in a much more elegant way. Because our original idea still used insights from symbolic regression. And when we had many variables, it was really a problem. We had no natural way to deal with variable selection. Also, the space of equations was growing super exponentially, and this was really a challenge for us. So we built a large language model to do all that and discover transparent dynamical system from data. How did we do it? This agent is passing through a set of iterations. It starts with the problem description and the data. And then it's proposing a first model together with a few variables. These variables could be either completely generated by the large language model, or if you have information from scientists, they could be informed by that, so clinical scientists or pharmacologists. And then the model is evaluated on a holdout data set. The large language model is reasoning about the model being found. And then we pass to a next iteration. As we are having more models, the question of how to combine models comes. So then we have a reasoning step that you can take a look in the paper that combines these different models, decides what features to select additionally or deselect, and is reasoning about, again, these combined models and evolving them over time, all the way till either a particular threshold has passed, we have enough iterations and we don't want to go any further, or a particular error, the model has an error that is below a certain threshold. What is evolved at every step is a symbolic program. This symbolic program is leading to a transparent equation, yeah? But this system talks symbolic code. What do we discover? Many things. This is just one example. One area that's interesting and was to my surprise, there is public data set on warfarin, and the PK model for warfarin exists for many decades, but is not very good. We discovered a better one, which has a better, let's say, estimation of how much dose and how much dose should be kind of the response to dosing for pharmacokinetic measures for warfarin. And you see there the original model, you see there the transparent model, and if you want to do hybridization, this agent is also able to feed the data even better if you don't insist on transparency, but we usually insist on transparency. And we put this model in front of pharmacologists, clinical pharmacologists, clinicians, and they were quite excited about it. With a clinical with a pharmacologist who is coming from France, actually from University of Limoges, we are now proceeding and trying to build this further. And together with AstraZeneca, we are trying to pursue this further as well. Now, what have we learned from this? We learned first that unlike conventional large language models that just respond passively to queries from the user, this LLM agent is able to be given a task, build a transparent pharmacological model, and it operates autonomously, iterating over time, and this is done without the user continuously prompting. The task is given, and then the agent is itself initiating queries, retrieving data, calling APIs to achieve the goal. Another thing that the LLM agent does, it's goal-directed. Yeah, so we give a high-level objective, but then there are sub-objectives, for instance, how complex the model should be, how many variables should be included, and so on. And all of that is kind of reasoned and built by the large language model itself. And over time, I'm showing you here a model that already it's 1 year old, but over time we evolved from less sophisticated reasoning methods such as chain of thought and process supervision to really more advanced ones in recent times. And it is on this topic of reasoning and adaptation that a lot of advances are happening recently. And what's interesting about these large language models, including the one that I just showed to you, we call it boringly D3, data-driven discovery. But the D3 agent has meta-reasoning and these adaptive loops where it is really combining models, evolving features, and reflecting on the strategies that were built to evolve new models. So this iterative process leads to more reliable results and more generalizable results. And the large language agent is itself doing that. We no longer need a human to pass through this process of evolution and debugging. Let me now move to another example of building digital twins with large language models. I'm going tomorrow to give in Francesca's lab another talk on large language models, or not large language models. Actually, I'm going to go beyond large language models on digital twins. So if you are interested, please find out where it is. But these digital twins are dynamic virtual representation of a system, and they are using data and knowledge to really try to simulate how a system would behave. Digital twins exist for a long time. Definitely in engineering, we have had a lot of them. But I used to have them when I used to be a communication engineer 25 years ago. But now, what's interesting about them, these models are no longer really only mechanistic. Many of them are data-driven, so it's really quite exciting. We can have digital twins in medicine for everything under the sun, from an organ to a patient, to a healthcare system, to a clinical trial. And they are not only in medicine. So digital twins are generative models, so they are more complex than just predictive models. You know, generation is always more complex than prediction. But the reason they are so interesting is because they tell us something about how the system would behave under interventions, and in the short run, in the long run. So this is actually very useful because if it is to debug our strategies for intervention, for planning, we want to have such digital twins such that on behalf of the patient or on behalf of the healthcare system, we can first test and stress test these interventions and plans to decide whether indeed we want to implement them in practice. So I'm excited about digital twin. Francesca is excited about digital twin. I hope all of you will. And again, they help us understand complex dynamic patient journeys. They help us test clinical hypotheses safely and rapidly before taking them to the real world. And let's be honest, machine learning often fails because we don't stress test it enough. And it's really important, especially if we want to act, because if there are complex plans, we want first to stress test them through these digital twins and then only at the end implement them. This is also important in medicine because I, as a patient, may want to understand your plan. Too often, clinicians just give us a plan, and maybe that's not the right plan for us. So we need really to understand stress test, and there is an increased discussion of patients and clinicians collaborating on the type of treatment that is given to them. And digital tools can form such a nice discussion, if you like. They provide a good way to have this discussion between patients and clinicians. And not at the population level, but at the individual level. So digital twins enable reasoning about the possibilities. This is not certainties, yeah? And in clinical thinking, often you do this hypothesis planning. So it is really useful for the clinicians to debug their thinking. It's useful for patients to understand what this means and what alternatives are. We started to build digital twins for medicine. Long ago, we used to build mechanistic one for communication systems, but now we started to build data-driven digital twins. And again, it's the two engineers in the lab. I'm an engineer as well. So it's the three engineers that got excited about building digital twins. So we built a hybrid one. The reason we call it a hybrid one is we use mechanistic models, models that come actually from knowledge that clinicians or pharmacologists have. And we embed this one with real-world data from electronic health records to build such twins. Why don't we go completely data-driven? The reason we didn't go completely data-driven was we had very limited data and we wanted initially to see how this works. More recently, we do more adventurous things, but that's something I'm going to talk tomorrow. Today, I just want to show to you an example, partially because I want to show to you how we built, again, a large language model agent to build such a digital twin. So again, you see this process, this iterative process that often LLM agents pass through. And what we have here is, again, a generation of a model specification. So we need to be very careful now on the model specification. And the user that starts initially with this model specification may be very ambiguous, may be very ad hoc. So this is why we often inject initially some prior knowledge. This prior knowledge can come from papers or can come from knowledge that pharmacologists or physiologists have. So this is what we gave to the problem specification as well. Then as this thing evolves, we are optimizing this hybrid model that not only contains the mechanistic model, but also the data-driven model. And we are fitting it to the data. We are evaluating the digital twin and reflecting on it. We get feedback. The human is in the loop in this case. So we wanted to see what happens if clinicians are actually involved in building their own digital twin. So there is feedback, not at every step, but every so often there is feedback. So the twin is actually tested not only on real data, but also it's tested through interaction with the human, which happens through natural language. And after multiple iteration, when the clinician is happy, we finish the digital twin. And we are applying it then to new patients. Oh, sorry. Okay, so I'm going to stop here about this, and I want to show you one more example and then summarize what this means for agents. The earliest thing we have done, and this is really at the very beginning, now everybody has heard about the fact that LLMs can code. But when we started this in 2022, very few people knew actually that LLMs can code. And I didn't believe LLMs can code, but again, it's an engineer and a computer scientist, so Sam and Max, that convinced me that LLMs can code. And I will tell you why I felt that LLMs cannot code. I thought that as the code becomes more complex, they won't be good at debugging it. And it is exactly the debugging process where we spend a lot of time improving. So again, this work is quite old, just appeared last year, but it has a history. And the focus has been on extensive code generation. The reason this is hard is because transformer-based architectures are constrained in their context window, and they excel at generating text, but text needs to be less rigorous often than code. Code needs to be semantically and syntactically correct. And context window size, it's what's usually the challenge, and they struggle to do that. So the question that we asked ourselves at the time is, can we generate large code bases that are correct syntactically and semantically? And this is why we started this L2MAC, which is an LLM automatic computer. At the time at which we started this in end of 2022, was the first practical von Neumann machine. So it's a practical LLM-based general purpose stored program automatic computer. And what was interesting is that this was our first LLM agent and was already multi-agent. Actually, the reason we needed to have a multi-agent approach is that as the code was getting more complex, we needed different types of agents to build different types of subroutines and test them and talk to each other to build the coherence of the entire code. So we have two components, the instruction registry, which is populated with a prompt program, and then a file store to keep intermediate outputs, and then link them with each other for the coherency of the program. At the time at which we started this, it was state-of-the-art, and it was the first agent for code generation to go above 90% performance improvement, accuracy, 90% accuracy. And this is on the benchmark human evaluation. And what was interesting, it was the fact that automatically self-corrected. It debugged and self-corrected. So it tested for syntactic and functional errors. When it found it, it self-corrected itself. So I'm really especially proud for this part of the work. And conditions and integrates on the existing previously generated code such that the code evolves and it becomes longer and longer to solve the entire task that it was given. This is the result that was there at the time. This is September 2023 when we first put it on the archive. And everybody else that was working on that at the time was just a few big companies. So again, what this L2MAC does, it's taking these LLM agents, which are actually building part of the code, and it's evolving it step by step, routine by routine. Every time an error occurs, the code is regenerated, retested, and integrated. And because we are building it step by step, this issue of making sure that the context window, it's not a problem, it's inherently solved. As I mentioned, what's interesting is the control unit, and this is really, I would say, something that we still need to work on as we are trying to build more and bolder programs, whether it's computer programs, whether it's symbolic programs, like I showed you before, with anything. We need to make sure that we have good control units, and again, this is where engineers are usually pretty good. We like to build things for that. And again, what's needed is to decide on what to test, when to test, and how to test not only sub-modules, but also joint modules. So what we built in L2MAC, it's a quite complex control unit and quite sophisticated and adventurous one. So this is not just Monte Carlo tree search or process supervision, which we currently do in reasoning, in agents. This is something even more sophisticated because it decides what to check, when to check, how to jointly check things. Okay, and this is really what, at the time, how this differed from reflecting LLMs, autonomous LLMs, both in context handling, in dealing with external memory, and very robust checking of the quality of the output. Because there's no point in putting code out there that's useless. And again, this is just showing at the time that you see, people were benchmarking. This was a criticism we had in our work. People were just benchmarking lines of code written. And we felt this is very bad, because if you just put lines of code, many of them may be erroneous. So we wanted to say this evaluation benchmarks are not good enough because just show the lines of code. But we need to show lines of code and accuracy, but also we need to show functionality, all the features implemented. How complex is the program and how many cases it is able to deal with. So we have lines of code, we have number of features that are functional features that are implemented, and how many tests it has passed. So we proposed a more robust way to test programs. Okay, so what is really happening here from an LLM agent point of view? On one hand, we can maintain persistent memory or state across multiple interactions as this code base is growing. We track and check evolving goals as well as user preferences, so the user could intervene in this code generation. And also, depending on what has happened so far, we can evolve the program in different ways. Reasoning and adaptation is important. We hear a lot about LLM reasoning, but what's interesting here is that we really need to have what I call meta-reasoning and adaptive loops to detect errors, to refine strategies, to refine outputs. And what's really interesting is that these iterative approaches need to have some notion of when to insert data, when to ask the user, which may be busy, to accept or reject a particular course of action. And how do we really test? Testing, testing, testing. A big thing in engineering, a big thing for these LLM agents as well, and an opportunity for new research. And then task persistence and life cycle. Right now we talk about one line, one code, but often you may want to have multi-threading, you may want to have more complex coding. So how do we manage long-running tasks, and how do we store partial results? And you saw an example in L2 Map how we build more and more complex programs. But really, how can we build extended life cycles, especially as we have multiple inputs, multiple data sets, still remains a challenge and an exciting one. Okay. Let me now talk briefly about how can we build clinical pipelines. And I've always tried to work very closely with clinicians. And again, in another talk that I gave in Milan not too long ago, we talked about how can we build risk scores. And this was not actually on Francesca's invitation, it was another invitation, so I keep coming to Milan. And that was a more statistical crowd, and what I was trying to say is we really should stop these quarrels between statisticians and machine learners, because the reality is we need to kind of join forces to solve problems for clinicians, and building clinical pipelines is one example. And something that we believe in our lab for almost a decade now is that we need to use automated machine learning to replace ourselves in order to impact clinicians. So if you look at papers that appear even in the top journals like Lancet or New England Journal of Medicine, often people use very naive analytics. They handpick XGBoost or a particular convolutional neural network, they do an analysis, they do some SHAP, and then they declare success. This is not okay. We have much more sophisticated models. We can do a lot better than that. We have complete interpretability that goes beyond SHAP. So we really need to do better. And there is no way for people who are working in informatics or the clinical world to keep up to date with the many advances we have in machine learning. The way to do it is through AutoML, where we are replacing ourselves, the machine learners and statisticians, and building these frameworks such that the clinical and bioinformatics community can use these models. The early work that we did was autoprognosis, which was a first AutoML framework for clinical scores, which built entire pipelines from data wrangling all the way to analytic building, all the way to interpretation and explanations. Has been used at scale in many diseases. Here are just a few, but really many, many people used it. This pipeline, this automatic pipeline, including was one of the very first risk prediction score for UK Biobank, which we built in early on for cardiovascular disease, which led to very interesting results for subgroups of patients, for instance, for the diabetic patients, as you see here. We also used it for the plumbing, trying in the pandemic. We were the first group in the pandemic to use this AutoML, to use any machine learning, actually, to help the pandemic in the UK. It was very bad, because in the UK, unlike in Italy you understood the magnitude of it. You had an initial bad phase, and then you got it. We never got it in the UK. We denied it, that it exists, till the numbers were so bad and the hospital were so overwhelmed that they had no idea how to deal with capacity planning. So we joined forces not to do highbrow medicine, but to do really the plumbing of medicine, to predict how many hospital beds will be needed at this location, how many ventilators, and how many ICU clinicians. And we repurposed, because AutoML can really feed any type of data, so we fed logistic data, operational data, to make these predictions. And this is an announcement from NHS Digital about the work they have done with us. We improved this over time. We improved these pipelines over time. We improved the software over time. And at some moment in time, the software was becoming so powerful that we thought, why is not everybody taking this? And initially we thought the reason there is not enough uptake, there is uptake, but there was not transformation, was because we didn't have enough tools. So we improved, and we have tools for survival analysis, time to event analysis, prediction, time series prediction. We also have treatment effect estimation, imputation. So AutoML for almost everything under the sun. So why not? Well, we thought maybe people don't know about these tools in the clinical world. So together with the collaborator, a clinical collaborator, we wrote a paper for Lancet to say, use these tools. They are very easy to use. They contain state-of-the-art tools. Everybody can bring their own tools, whether are statistical or machine learning. And it has a lot of advantages in terms of usefulness, of model performance, of transparent reporting. And the frameworks are open source, so you can easily see what other people have done. You can bring in your own work. You can evolve. We have uncertainty quantification, pure transparency, not black box results, transparency. Why do people not use them? Or not use them more, I should say. And then finally, we realized it's because in the end, these packages are superb, but they are requiring you to know a little bit of Python, which most people don't. Even though we explain things, and I need to say quite a lot of clinicians taught themselves this minimum Python to use them, still, it takes, the clinicians especially are very busy. Learning Python in their evening hours is not fun. Luckily now we have large language models, so suddenly we no longer need them to learn Python. They can communicate through natural language processing. So we can build copilots, clinical copilots, such that clinicians no longer need data scientists, statisticians, and machine learners. So finally we replaced ourselves, or at least I hope we do. So we built together with a surgeon that cannot code, Vasilis, who's a surgeon in Cambridge, an engineer, a medical student in Heidelberg, and a PhD student of mine. We built Climb, which is a partner for clinical predictive analytics. And then we built another one together with epidemiologists. And what in Climb we do, we put under a natural language interface, we built a copilot that's an agent that takes many tools, takes data-centric tools, takes prediction tools, takes transparency tools, and in a discussion with the user, which is the clinician, can really build an analytical pipeline. And I really hope to convince all the statisticians and the machine learners in the room to join forces with us to put more tools in this open source package, such that we really can replace ourselves and do something more interesting. And then let the clinicians really now take the ownership to build these tools. And probably the biostatisticians, because maybe they still need to vet what has been designed. But speed up and scale up. Okay, so again, the clinician now, like with ChatGPT, they can really talk and converse in natural language. But this is not ChatGPT. This is a copilot that uses natural language but has many, many rigorous tools underneath. And it's an entire pipeline that is built and very carefully built underneath. We have dashboards, we have explainability, we have everything is stored, so you can debug the code if you want, somebody can provide the code. Also, this Copilot is writing a first version of the method section of a paper, so everything is there. And the interface is really quite beautiful. It has a session management, it has a dashboard. You can discuss through natural language, you can create multiple versions of your favorite risk score, and everything is stored such that somebody can inspect it afterwards. And what's also important about this, it maintains complete privacy. So when we built it in such a way that the data, which is often clinical data, is not sent to OpenAI, which is something we really don't want. So unlike the baseline, which is the sophisticated GPT, we are able to have robust planning, advanced memory solutions, a much more informative dashboard that contains graphics, that contains analytics that are shown there, and also the data is kept private. We let 40 clinicians play with it more than a year ago when we started this project. Actually, at the University of Amsterdam, we decided to join forces. Actually, I'm saying this for the sake of Alicia. We decided that the people in Cambridge are slower than the people in Amsterdam, so we decided to join forces with Amsterdam Medical Center. So we are going to run some sessions with them, and we hope to join forces to scale this to the next level together with them. Maybe we can do that in Italy as well. And the original version, we put 40 clinicians in front of it to compare CLIMB to GPT. And they much preferred it because this is not just GPT who invents all sorts of things, but rather that in this agent, this CLIMB agent, this Copilot, we have a very clear, very systematic pipeline of building these analytics. There are a lot of error checks and a lot of tools underneath, which are invoked by the Copilot as the analytics are progressing and as the user asks questions. Among them, we have an interesting reasoning capability. I'll just say a few words for the machine learners. So unlike just doing Monte Carlo tree search, the trouble with, so again, for the reasoning people among you, we have a lot of Monte Carlo tree search, process supervision, many problems with this because we have very long traces and just a reward model doesn't exist. We have a lot of intermediate rewards that are important. Also, just saying, I have a performance, which is error under receiver operating curve about this value is not enough because often you need to make checks because what you may have often in medicine is data leakage. You think you have fantastic performance, but actually you have big problems with data leakage. And often because of these long horizons and multiple steps, the performance of Monte Carlo tree search and process supervision are bad. So we built actually a quite sophisticated reasoning engine for this Copilot. And you can read about that in the CLIMB paper, which is online. But even more exciting, if you are a clinician in the room, please take a look. The original version is online. You can play with it. The more sophisticated version, we plan to first debug it at scale with the University of Amsterdam. But as soon as we do, we plan to put it online. And there are some sessions here where you see how clinicians have used it and so on. Okay. So I think in view of time, I'm going to kind of try to just say, where are we now in terms of this? You see that agents in this Copilot case are becoming much more goal-oriented and can do long-term planning. You see that they can involve tools. In this case, they use analytical tools. They use tools for data-centric analysis. They use tools for interpretability. So they invoke tools as needed. So they don't just generate code, which may be generated on the fly and not of high quality. They invoke tools that already exist and are very well debugged. And it is only the high-level planning that is done by the agent. And while I won't have time, unfortunately, to tell you too much about genies, I just want to say that while LLM agents are exciting, and I showed you some examples, I really don't believe that it's enough. We need to build something at the next level. And I call them genies partially to differentiate them from AI agents. I put online discussion paper especially for the machine learners in the room. So if you're a machine learner, please take a look. I'm really trying to kind of convince the machine learning community that needs to go beyond just these LLM agents. And there are many AI problems and ML problems that we need to solve. And what we need to do is we need to build a much more comprehensive engine, if you like, of self-improvement that does innovation, operation, validation, evolution, and empowerment. And this, if you like, engine of thinking needs to evolve over time. Right now, as you see, I built an agent for discovery. I built an agent for coding. I built an agent. Ideally, you want to have these genies that co-evolve with an individual or co-evolve with an organization, and they are multi-capable. And also are able to be proactive, real partners in thinking for the human. From that point of view, genies go beyond LLM agents, and they aim for this comprehensive long-term synergy with the humans. Multiple capabilities going beyond what you see in agents. You can see an example which I wrote together with a few clinicians about how the future of medicine can look like. Please take a look and help me develop another version if you are interested in. We also are searching for people to help us develop one for business. So if you are somebody with interest in business, help us, please. Envision the future. And finally, for the machine learners in the room, I'd like to ask you to consider taking a look at these questions and maybe try to answer some of them. I put 101 questions and people said, why 101? Well, I had 160 when I started. I already cut a few. And I think that answering every question that I have in that manifesto is challenging. So if you are a PhD student searching for a good problem, I think every question in that manifesto discussion paper is a PhD thesis work. So please take a look and hopefully get engaged with the Genie agenda. Thank you.
Thank you very much. I think it is reductive to say that it is an inspiring talk. I hope that we have some time for questions. There are two, so I go beyond and then I come to Pablo.
Thank you for the beautiful talk. I have more of an ethical question, let's say, about AI agents and about high agency in manipulating medical data, for example, genetical data, and especially if you're going towards genetic engineering. Do you think, are there any risks about high agency in this world, and how could we prevent them? Thank you.
Thank you. Thank you for this question. So first, I'm not talking about genetic engineering. I'm talking about Gen AI and medicine. There's no genetic engineering here. Clearly, we need to be very careful, and ethical frameworks are very important. We work with ethicists at the University of Cambridge when we do that. We also, that's the reason why you see privacy of data is very important. So we work quite a lot to keep this data private. I think that is important to advance the world of medicine. I think we are still in a stone age, I would say. We make a lot of advances, but we still don't have discoveries. We still don't understand many things. We don't understand how cells fundamentally work. We don't understand how the human body responds to multiple drugs. We don't understand really treatments that are given to us. So I think there is an enormous need, ethical need, to build technology that's empowering for humans. I'm mainly interested in building AI for medicine and for education, which are two areas that really need empowerment. I'm feeling less happy about AI in other domains. Let me leave it at that. But another thing I want to say is that we are trying very hard to work together with stakeholders. So really clinicians on one hand, educators on the other hand. So we are unlike maybe other labs in the world which just go do something. we are trying very hard to build solutions for problems that exist and that the clinicians really try to solve. So ethics, important. Stakeholders, important. How much autonomy you should give, I think also important. So for instance, for this copilot, we decided to make it very compliant to the human. And there were a lot of criticisms from my students initially because they said, well, non-stop we asked the human to vet or validate certain things. And we decided to go for that particular choice, both because of ethical issues, but also because we realized many clinicians got so enthusiastic about building their own AI because suddenly many of them never saw their data. They always had the biostatisticians or the epidemiologists dealing with their data. Now, for the first time, they could see their data. They could visualize their data because they were able to just use natural language to ask all sorts of questions. And at times they were surprised about what they have and don't have in the data. Also, as they were building their analytics, we saw that in their enthusiasm, some of them made a lot of mistakes. So part of the reason prompting the human to take it easy and think and maybe talk to a biostatistician is to make sure that they don't just run with a problem and maybe build something that's useless. So I think this requires ethics, requires thinking, requires interdisciplinarity, but I think it's exciting, and I think in the area of medicine we should do it because, as I mentioned, medicine is still very much an art. We have good drugs, but we don't know when to give them, to who to give them, when to change them, how to combine them. Medical pipelines are still quite one size fits all, so I think we need technology to be built, but it needs to be carefully built, as you rightly said.
Thank you.
Thank you very much. I'm speechless, but nevertheless, I ask a question. The question is about LLM agents. And let's say the question is, do you need domain-specific knowledge to, let's say, fine-tune or train these agents? And if yes, what do you use? How do you do that?
It's a very, very, very good question. And I will tell you, I don't know the perfect answer. So I will tell you, I'm thinking on my feet because I think your question is very important and I don't have the perfect answer. So the way we did it right now is, you see, when you build these agents, you need to give them capabilities. You kind of, almost like a robot, you endow them with certain capabilities, certain abilities to deal with data. You are kind of designing some of these pipelines. Certain things emerge, but certain things are designed by us, at least at this moment in time. In the Genius case, we hope that they are going to self-design. But right now, we are kind of playing the engineer of the system. And we have done it in different ways in different agents. So for instance, for the clinical copilot, partially because of what was just asked, we design it with either a clinician or an epidemiologist at our side, and they helped design this pipeline. In another case, in the discovery case, we completely let the large language model read a lot of papers about steps that the specialists took, but then it just stole these ideas, if you like, and built itself. What's better, I don't know. How to combine these approaches, I don't know. Exciting times, I think.
Thank you very much. Yes, there are last two questions, and then I will.
Just you know, I'm totally overwhelmed by your speech. So speechless as.
It's nice to be in Italy because people are so polite.
But let me say, I was thinking, okay, shall we go on teaching our students equations, mathematical models, mathematical reasoning, or this will become topics only for history of science course, but not really for science course?
Another complex question. Let me start somewhere very nice. So, I was very honored to receive an honorary kind of award from the University of Amsterdam, the Spinoza guest professorship. And what I decided to talk about is no equations needed. And what will make you funny, what will be funny about it is that the person that worked on it was, I have 4 mathematicians in the group. And I need to say they are some of the very best students I had. The best machine learners are actually pure mathematicians that couldn't code when they came. So on that note, I'll come back to it. But the person that helped me do this work is actually somebody that studied pure mathematics and was an Olympic in mathematics. And the reason we started to talk about no equations needed is because we realized that we often say equations are transparent, but then most people can't as the equations become more complex. And our stakeholders are clinicians who hate equations. So we increasingly started to evolve and talk about trends, talk about motives. So that's more on that note. But I do think mathematics is needed. I think mathematics is needed both because it enables the few among them, I should say, because I'm an engineer, mathematical engineer, I'm not a mathematician, but the mathematicians, the mathematical engineers, I think we really need to be able to debug, to test, to analyze. So I think mathematics are still important. We need to verify what's happening. We need potentially to advance the area of mathematics. Can these genies really advance the area of mathematics? Maybe not. And I also hope that we humans stay creative and stay in control. And this is where I feel that maybe not humans, maybe not machines, but we together can work together. And I hope that we can build this kind of future of science where humans and machines can co-evolve, coexist, be prompted. So I don't know about you, but I've learned, partially from some of my students, to brainstorm with large language models. So I'm brainstorming a lot. And at times, they give me fantastic ideas. At other times, they bring me into some hole that actually is useless. But I think that I like always to brainstorm with my students. I spend, as Luca will tell you, hours interviewing students, days interviewing students, partially because I want them as discussion partners. But nowadays, in addition to my brilliant students, I quite a lot brainstorm with these machine learning models. As they become better, I think they'll become fantastic discussion partners. But of course, that has social implications, has questions about what we should teach, what we shouldn't teach.
So you don't foresee a risk of developing an alien science, some alien meaning not human, that we are totally detached from it?
I find that this is why I want to change the debate. There are too many people that want to build this AGI, they want to build all sorts of things, and I don't know for what. So this is, I kind of like to have goal-driven. So I'd say, let's have these genies that are empowering a clinician, a clinical system, or an educator to teach better math or medicine. Complex.
Last,
long dinners, coffee.
last quick questions, and then I will left the other questions to the coffee break.
They are more suited for the coffee break anyway.
Okay, thank you for your talk. I have a quick question about your experience since you were talking about, I think we as an engineer most of the time are obsessed with technology part, and we take care less about the practice and the real world. I mean, as an engineer, how I want to know about your experience, how you make a relationship and how you try to make a trust between practitioners and engineers as a translator, and to what extent you try to talk with their language to help them to adapt this kind of technology, since when you're talking to a practitioner, they think that most of the time these AI models are black box, but in generally speaking, we know that they are not black box because we can present the parameters of the model. I want to know I know that it's not a straightforward question, but I want to know about your experience.
This is the billion-dollar question, I think. I think your question is the billion-dollar question. So I try very much to understand these other worlds that interest me. So I'm not interested in games. I'm not interested in playing computer games. I'm not interested in robots. But I'm interested in medicine. I grew up in a family of clinicians, and I often felt that they are more artists than scientists. I'm also quite interested in education. So I'm trying to really, I spend a lot of time talking to clinicians, finding those clinicians that want to teach, they want to understand. I'm at times disappointed by my own students because not everybody wants to have these long conversations. And I'm trying to teach them that in order to stay relevant and do something useful for the world, they need to engage in these long, complex conversations in which we don't understand each other. And we need to try to understand. We need to try to explain. Not always an easy job. At times I'm quite forceful in my students and I say, you must do this, and they are unhappy. Hope Luca is not running away now. I feel that this is what will keep us relevant. Now, I know that, how many of you are engineers in the room? Raise your hand. Okay, thank God, so probably I will not be killed. So I think that we engineers are going to be relevant for a longer time than many other disciplines. And partially the reason we are, so I can tell you, I have an edge doing AI. I used to be a pure engineer. I did comms, I did smart grids, I did multimedia signal processing, and I moved to machine learning, and I do really well. And the reason I do really well is because I'm an engineer. And I can smell things. Yes, I won't have the billion citations. People at times come with an algorithm that's another algorithm, everybody uses it. My edge is trying to look at the real world and try for the first time to solve the type of problem. But I always have ideas. I'm full of ideas, partially because I'm looking at the real world. So I think we need to engage with the real world, try to understand where is the need for a problem being solved, engage with it and try to evolve machine learning and the engineering framework that comes with it to evolve it. So I'd say the engineers in the room, let's come to the machine learning world. It's so needed, your perspective in engineering, in machine learning. We have too many computer scientists and that are just building algorithms. I think that's important, but I think it's also an opportunity to take more real world problems, trying to understand them, trying to bring them to this real world, and try to and also another thing that I hate in the machine learning community is this obsession with novelty. And to them, novelty means I come up with a delta on an algorithm. Well, at times novelty is talking to a clinician, understanding something complex and saying, oh my God, I don't know how to solve it, or solving an ethical question correctly. So I think we need interdisciplinarity, we need, I don't know, we need to think. And that takes a lot of time and not everybody wants to do it. So in more recent times, I interview my students for this desire as well. In the past, I only used to interview how smart they are. Nowadays, I'm doing 2 more interviews, and one, how good a fit they are with me, because I'm a strange advisor. And number 2, how interested they are to talk to others outside their ML bubble. And I can tell you how many say, I'm not interested.
So let me thank Mihaela again, also for this work.